does it here? Hi, good morning. We still have the attendance sheet. I actually found several people who did not attend. Actually, was those people already, they already dropped the class. They just removed the name. You probably can see, if you see the last time or last week, the assignment, the attendance sheet sign up, you get more people have more marked points. Actually, this time we have very few because those people who did not show up, they already dropped. Okay. Just to remind everyone, if you happen to come late, you still need to try to finally find the sheet you sign it, because otherwise there's no proof you are in class. Okay. Before we start our lecture, I should have one announcement. Is we have the assignment 1 available. You are responsible to do this assignment. Okay. If you look at the due date, you say, oh, this is 1 month away. There are lots of time. You don't have to worry about it. But I should say, even there are just 4 questions. There's one question, actually, the last one is a programming assignment. That will take some time. So that's the reason I strongly suggest you to start early. Okay. For this program assignment, mainly is doing similarity search in heterogeneous information networks. And that one we are going to discuss in the lecture next week. Okay. But there's one interesting thing we actually tried, because the TA gave this assignment. He himself actually tried it. Okay, not just to ask you to do it. And it's interesting is we use, because our group proposed PassSim, you are going to learn it. There are 2 rival algorithms, one called SimRank, one called personalized PageRank. Both were proposed by Stanford University. We originally want you to try one SimRank, one personalized PageRank. Then the TA tried it, said the SimRank was so terribly slow. He actually tried to just run on the same data sets, just one iteration, not to say many iterations until stable. One iteration, it took all his memory, his machine's memory, and took all the time. He ran several hours, could not get any result. It's too slow. Okay. So we finally said this is not realistic, even to run on a very small subset of the DBRP data. So we think it's not a real. We cancel that one. So you don't have to suffer running out of memory. Okay. So we only ask you to compare PassSim and personalized PageRank. Okay. So that's the reason. If you happen to watch yesterday's assignment, and today's one is different, because this morning, once TA reported me, you just cannot finish. We just change it. So this morning, it's an updated version, and it's right. Okay. If you want to try early, you can try it. Okay. If you see what should be the output and what should be hand in for the program assignment, we want to hand in the source code and the running result as well. Okay. Simply says if you just say, we just need, say, 10 names for each author, and this one is 10 names. You say, oh, I just need to know these 40 names. I just put it in. That's it. We want to see what's a program you really write. Okay. Instead of you just watch others got 10 names, you just put it in. Okay. So it's a lot of interest, a lot of fun, because you see the real people. Like we took Christos Valoutos, Ang Haiduan, like David Bly. Those people, you all know them, hopefully, at least after this class. And then you play with it. You see how they, who are most similar to them. So you probably see you get a lot of real cases. Okay. As Johnny suggests, you start early. Even we just published, we say there's 1 month away to work on. You should read it. You have any questions, you raise it to me or in Piazza. Somebody will help you. Okay. Especially if this one has any minor errors, we can correct it quicker. Okay. Like this one, unfortunately, TA first run it and knows it's not going to finish. Okay, so that's the reason we actually, it's good you first try it. Okay. So this is about the assignment. Any questions? The question is whether it's group work or individual work. This is the absolutely individual one. Okay, this is the assignment everyone needs to do. It's not like a research project you can work as a group. Okay, so this is like an exam. You know, it's everyone, you have to do it by yourself. Okay, of course, some discussion is okay. You can discuss with your classmates, especially for program assignment. If you have anything not fully, digested on the course material, you can discuss with the classmates. Okay. Discussion is allowed. Copy is not. Okay, it's independent work. Actually, in the past, sometimes we did catch the case, the copy of the other one's assignment. Remember, you'll be fully responsible to protect your own answer. Okay, otherwise, both sides may get penalty because we were thinking you two were playing the trick, one copy the other or something. Actually, the penalized sometimes it involves both parties. You try to make sure you don't say I got it, I finished, I just give the whole thing to my friend by email or by hard copy. That's not good. That's considered as a misconduct. Okay. Any other questions? Okay. Yeah. Like we said, this one, we encourage you to have some discussion, but finally you have to work out independently. Okay. So that's the assignment. We have 2 assignments in total. Okay. So this is the first one. This one, hand in, I think it's just 1 day before, a few days before the midterm exam. I think it's just 2 days before the midterm. So this is a good review. You have a better digest of the materials. Okay. Now we will come back to what we discussed on the modeling of network formation. Okay. The general idea is the network was not generated randomly. In most real network, you use random model, it will not fit. Okay. And we actually give you a few general properties. The network has very few connected components because everything almost connected. And you have very small diameters just because it's very dense, things are interconnected. It has high degree of clustering and heavy tail follow the power law. And we give you a few formulas. Okay. Formula, the first one, we said small word property simply says just because the real network is reasonably dense, you have one thing connected, you can reduce the diameter. You think about this. Okay. If you connected to somewhere, like I connected to a professor in University of Pisa, okay, that connection is direct connection because we have communications, we know each other to some extent of friends. Okay, then he may connect it to someone in say Florence. Then I have the connection. The diameter actually could be very small. So that's a small word property. Okay. Then you probably can see the small word property. You can actually measure the diameter to say the path length and average path length, how long it is. In many cases, the measure is log n. That's a small word. It means it's really, you get that many, like you have 1 million But you take the log, it just becomes 6, right? So that's why you take log. But in many cases, you may even take double logs, okay, or much smaller than the single log. You think of the web. The web has not just 1 million; it's a trillion or even more nodes. But once you take, even for Yuri Leskovich, he did experiments. The average length for the IM messenger, this thing, IM is 6.6. Okay, simply says even you get billions of people, 100 million of people, you take a log, you probably want to take a log again. It's very small. Okay. And the scale free simply says you double your nodes, you times k times n, but actually it will not really take you even linear time. It's almost constant time you can get it. So that's what we call, because the nodes have very small degrees, then the probability node has degree k. Actually, it's pretty small. This probability has a particular degree. You can follow this. The interesting thing is, if you want to check this parallel distribution, is you just project it by the log-log plot. Then you will find a linear line, okay, or something closer to linear line. So then you will say this one is a parallel distribution. Okay. Another one is clustering effect. Clustering effect means because any nodes, right, you may share some common neighbor, then they likely will be connected. So you will have high clustering coefficient. Remember last time we discussed that you get a node, how do you calculate the clustering coefficient? You just take your neighbor, look at your neighbor's connection, and versus all the possible connections. Okay. If you get, for example, if you have 10 neighbors, if these 10 neighbors are all mutually connected, get almost a fully connected graph, then it's a very highly clustered. The cluster coefficient is 1. Okay. But in reality, of course, it's impossible that everybody is connected. You will have some potential edge actually missing. So your clustering coefficient is always less than 1. But on the other hand, if it's closer to 1, you will think those nodes really have clustering coefficient, high clustering coefficient. You have a clustering, like. So for parallel, actually there are certain nodes, they really, really highly clustered. Okay, so to that extent, you will find that some places they are highly clustered. Okay. Even the whole network could be very sparse. Okay. That means the whole network, you think of all the possible nodes connected to all the other ones, is impossible. It's very, very sparse. But if you just look at a particular individual, you may find some places it's very highly clustered. Okay. So that's a clustering effect. It simply says nothing is evenly distributed. Okay. Then we want to look at the probabilistic model. Probabilistic model means if you think this network's somehow generated, what kind of a model they really generate this network, like an internet. Okay. The very beginning, people study it. They use random network model. They generate something like a Poisson distribution, those kind of distribution. And finally, people find the real network is far from this reality, from your model. So it simply says a random model may not be working. Okay. So that means if we want to study the real network, we want to build up a probabilistic model to model this network. The model simply says you need a certain parameter you can set. You can set certain distribution, whether it's a Gaussian distribution, is a Poisson distribution, or any kind of distribution you want to model it. Then you try to see whether your generated model will match or somehow match the real network. Okay. And here I just give you some very simple review of the probability or random variables. Basically, you will think anything. You assume that there's a random number. You can toss a coin or something. You can get certain probability. You can get distribution. I will go this very quickly because otherwise we go into the basic statistic course. Right? Basically, is if they could be mutually independent or conditional. You can calculate their conditional independence as well. And there could be some expected value. Usually you use, the expected value is somehow have this kind of if they are independent, the random variable, the expected value have this kind of a relationship. You can calculate variance and standard deviation. And, there are lots of properties that will not give you the general one. Simply says, if you assume those variables are independent variables, you may have expectation is mu, the variance is sigma square. I think those are the general ones. And once the graph or data become really big, they will usually be normally distributed. So this is the central limit theorem. Okay. So the typical distribution that people studied in statistics, the most typical one could be Gaussian distribution, or some people call it normal distribution. Okay. And the distribution, you may have the density, and you have the graph, and we probably already, early days we already mentioned, if you got even 2 standard deviation away in Gaussian distribution, it covers 96% of the data. And the 3 standard deviation away, it's, after that, only 0.3 or something fall into those parts. So it's very, very rare. You can think these are outliers. Okay. And you can think that the binomial distribution is throwing the coin, you get head and tail. I think actually even this election, I was told, some caucus could not make a decision between Hillary Clinton and Bernie Sanders. They flipped the coin. Actually said Hillary got both of them. So it's kind of a luck, because otherwise, if you throw the coin head and tail, it should be evenly distributed, right? So that's the binomial distribution, right? If you see you throw 6 coin all favor to you, actually it's very rare. And their Poisson distribution, that's the one you get. It's also very popularly used. But we are not going to discuss those distributions because that's a very typical distribution studied in statistics. But there's one distribution actually was not really frequently introduced in statistics, but it's very, very useful in networks, called the power law distribution. Power law distribution originally, or alternative name called Pareto distribution. Pareto actually was a French statistician. Okay. He discovered this distribution. That's why people named under his name. But more exactly, this is more like a power law, because if you look at the distribution, it's really like exponential one. That's why they call it power law distribution. And if you look at this power law distribution, or some people call heavy tail distribution, is this. A small portion of data, like here you can see this X value is very, very narrow portion. This small portion of data, you cover huge, portions. Okay. But then it drops down very quickly. Then you get a very long tail. Even you draw this line really, really long, you still find some data. So, but it's a very small proportion. So that's why they call this one is a long tail or heavy tail. Okay. But on the other hand, this part of the head get most of the data. That's why it's almost in the power form. That's why I also call power law distribution. Okay. That distribution formula essentially is if you get 2 parameters, K and M, you want to see this probability. The probability follow this formula. This formula simply says, if you look at the distribution, the M here is more like closer to this this one. This is like a, for example, if you think, if you strictly follow this formula, okay, when k is 1, you can see you get the blue line. This line is k equals 1. K equals 2, you get this. K equals 3, you get like a pretty sharp one. We only listed these 3. And this formula basically says that all the data is somehow linked to this. But if you think on the web, you may think there are a few nodes, very small number of nodes, get lots of connections. That's why they were along this line. Like, for example, you say Google.com or Microsoft MSN.com. You probably will find the people point to them, you get that many. It's really, really huge. Okay. But you get a normal nodes. For example, you yourself have the home page, say, how many people point to me? Probably a very small number. Right? That's the reason you probably see that this one drops very quickly in the connection-wise. And finally, even you get 100 million people, you still have something. Maybe only 1, or maybe something closer to 0. Right. So, but that's the reason you get this power law distribution. Okay. And the key is other things like a binomial, normal, or Poisson distribution. The tail probably approach to 0 really, really fast. You think about it. We already said you get 3 standard deviation, where is almost nothing. Okay. But here, you get a very long one, they're still not reaching 0 yet. They still have something. That's why it's a long tail. Okay. And then we will see when this mathematician Pareto first discovered this, what he was studying. He was definitely not studying internet. At that time, there were no internet at all. That's the 19th century, right? So, but they do have something, for example, word count. If you count even the English articles, you count number of words, you will find that certain words appear really, really frequent. For example, the or a or an, on or off. They actually come out exponentially high. But then you see those frequently used words, they come down a little lower. But there are some very infrequent used words, they still appear somewhere. They really form a power law distribution. And actually, they study the wealth distribution. A few people get billionaires. They got lots of money. But it's a very small number. But then you look at down the majority of people, you get a long tail distribution as well. So it's a very typical, very popular facts in many society or real world issue. That's the reason people found this power law distribution in real world could be quite true. Okay. So then let's see how we can distinguish the distribution of the data. That means if you got data, you get all the different things. You plot on the graph. How do you say what is the distribution? Okay. Actually, if you plot on the graph, if you use log-log plot, like we said, the power law distribution get a very nice line if they strictly follow the power law. Just because if you think of this power law distribution, the distribution is 1 over x to the power of alpha. Okay. Then if you take a log on this one, you get a minus alpha in the front, then this one becomes log x. That means if you think your original value is y, you get a log y. Okay. Here you can see this is log x. These two logs exactly form a slope. That's why you can see if you take a log-log plot, you get a nice line like this way, right? But if you take a normal distribution, Poisson distribution, take the log, you will find like this one, you will find that this one is not linear. So it's more like, like those concave or convex. The same thing as Poisson distribution, where you find that you take the log, you will not get the linear one. Okay. So to that extent, it's very nicely you can see if you do log-log plot, you nicely see a line. That's power law. Okay. Actually, besides this Pareto parallel distribution. There's another one studied in mathematics or also in computer science quite a lot called Zipf law. What is Zipf law? Zipf law, if you, I think anybody study performance evaluation on computer systems or database systems or any query optimization or this kind of thing. In many cases, you may find this Zipf distribution, Zipf law is very popular. That means simply says Pareto distribution is power law. Zipf law is also sort of power law. The only difference is Zipf, they look at discrete number. They not look at the continuous number. The Pareto look at the continuous number. Okay, so that's a major difference. Like when you calculate those corpus, you calculate the word count. That's a discrete number because you count 200 or 300. That's a discrete number. That's why the word frequency follows Zipf law, essentially follow the power law distribution. Okay, so they are the same thing. One is discrete version, one is continuous version. Okay, and now we look at the distribution curve. You probably can see. That's one people study. For example, this is one experimental result, so I think you can see this. This is a real one. This is the x-axis. This is y-axis. If you draw the distribution, you may draw like this. But when you look at a log-log plot, you draw like this. Actually, even when you do computer science study, you generate a paper, you want to study performance. In many cases, if you see the scale is too far away, for example, it goes exponential. Very, very easily you will say, oh, if the y axis goes exponential, I take the log scale. I don't take the linear scale because otherwise you draw out of your picture. You take the log, you bring it down, nicely. So that's a similar idea. Okay, but you take log on both, you get a linear line. Okay. Then later we are going to show you, like John Kleinberg, Crystal Falosas, they took the whole web, they look at distribution, they really draw a line, which the line log-log plot is really like a nicely follow a straight line. Okay. Then we look at the history. Okay. The history actually was not immediately getting into the power law distribution. That's after a while people realized this. Okay. In 1960s, or maybe even 50s, okay, we get back to this Erdős Rini. Okay, Erdős, I told you, he got this, like a traveling mathematician, keep working with many people, generate many papers. One of his famous paper, actually very popularly cited paper, is called a random graph model. I mean, he was thinking the graph or network was generated in a random way. What is random way? That means, suppose you get some edges, or you give me a graph. You say how the graph will grow. Okay, and his basically assumption is the graph can grow in a very random way. Means you pick up this node. The chance this node will link to any other nodes getting an edge, the probability is just by throwing a dice. Okay, you throw a dice, so you get a certain number, you grow that way. So whether two nodes are connected or not is purely by the random number. Okay, that's a random graph. Okay, so the graph was generated in this way, but the mathematically, it's kind of a beauty, right? You use a random number. You can writing lots of very nice formulas on how they behave. But once you match the real world, very rarely you get a random graph. Okay. So that's theoretically, even now, if you go to physics or go to certain journal in mathematics, they still study random graph model. Okay. They assume that the graph underneath mathematical model is random. But actually, this one now in the real network is not the case. Then the second proposal is Watts and Sturgatz. That's a one called a small world graph model. Okay. this one was proposed in 1990s. Okay, almost a similar years, just a little later, Barabasi Albert proposed a scale-free graph model. Okay. We are going to introduce these two a little more detail, especially Barabasi model. But I probably should say it's interesting is last month I was in Poland. It's a network science conference. I gave a keynote speech. And there are 5 or 6 people give keynote speech. One was Duncan Watts, one was Barabasi. Actually, these two are very well recognized. One in the network science community, they are the pioneers generating very long-lasting results on the network modeling. Okay. So let's first look at Adish-Rainey model. Of course, Adish already passed away. He passed away in 1996. He was generation older or earlier than the later one. They still, like Barabasi actually is pretty young. Okay. He's very active now. He's a professor in Northeastern and also Harvard. Okay. Actually, the student I mentioned, Yizhou San, we study her book. She currently is working in the same group as Barabasi. Basically, Barabasi grabbed her from when she was applying. Okay. So that's they're in same research group, same in Northeastern University. Okay. Adish-Rainey model was done in this way. Okay. I probably first show you the picture. It's better. Okay. That's Erdős. Okay. He passed away in 1996. You can see what his basically assumption is this. You got these nodes. You get the edges. How they are connected. Okay. They're connected by throwing a dice. Okay. And it's random. You get a different random functions. Okay, some could be linear, some could be, but you throw the dice or you run this random function, you will generate an edge. You can draw this. So then finally you get a connected one. You get a network. Okay, you can see the probability to link to the other one. You can use many different functions. There's no restriction. You can see this probability is 50% of n. This is 1 over n. This is 1 over 2n, 1 over n, 2 over n, 10 over n, log n over n. You can use different probability to generate this graph. Okay. Then, of course, they have different density, different clustering property. But overall, what you generated is sharply concentrated graph, but it's not heavy-tailed. Because everybody got the same chance. You think about it. I got a chance to link to the other guy. The other guy also got his chance. Everybody got the same chance. You will not be able to get a heavy tail. Okay. It's more like everybody will have a chance to generate the research paper. Okay, so everybody, when you do the evaluation, say everybody just the same because we do it randomly. But actually, in the reality, it's never the case. Okay, some very productive one, even like Adish himself, he generated 1,500 papers. You look at other people, they may generate only 2 or 3, right? So this, the word is not random, it's not even, okay? Then we look at another model called Watts and Storgard's model. These two scientists, Duncan Watts, actually, they have a 1998 Nature paper. Nature magazine is very prestigious. You publish there. Okay. And what they found is they found the original one, you got a small word property, short length, and high clustering. But you actually, he found this ER means Adish-Rainey model, the graph. In the real world, the real world may have, there are some local clustering, maybe high, but the overall clustering coefficient could be low, could be very sparse. You think about it, the internet, the overall, the sparsity actually is quite big. And another thing is they actually, you would think about this is power law distribution in the real world, but actually the Watts actually proposed one. They can generate small world, but it cannot generate scale-free graph. Okay. But because of this, I'm not going to introduce this one in any detail. You just know this one is one progress from pure random graph model towards small world one, then towards the scale-free one. Okay. And according to Watts and Storgat's model, that you can generate some different thing like a small world one, random one, a regular one. He actually shows the graph in many cases could be the small world one instead of pure random graph. Why the small world one is a better model than the random graph? Okay. Originally, you may say whether, of course, which one matches the reality better. Actually, the key originally, people starting from the random model, starting doing the patch, try to match the real network, but the patch become more and more complicated. And Watts basically say my model actually simpler, and I can explain part of the word, so my model must be right. Okay. That's also why those reviewers believe this, because there's one interesting general philosophy called Occam's razor. Okay. Occam's razor basically say, if you have lots of explanations of this phenomenon, I will take the simple one. Simple one likely to be right. Okay. That's actually, in science, there are lots of cases. People explain the same thing using many, many different ways. Okay. But finally, most people will recognize the simplest one will win. Just give you a simple example. This time I went to Poland. This is my second time I went to Poland. The first time was 2007. That time was the conference was in University of Warsaw, okay, and in front of the campus, University of Warsaw, there's a gigantic statue called Nicolaus Copernicus. I believe you probably study physics or anything, Copernicus. Okay, Copernicus was the one who first proposed instead of the Earth as the center of the world, he proposed the sun. Okay, that means. Originally is most people are thinking everything is surrounding Earth. Then they work out those planet. They work out very complicated function, the curves. Okay, very complicated curves because surrounding Earth, you think if the really surrounding sun, everything is like a circle. But if you think Earth is the center, it will become very complicated equation. Right? Those people, mathematicians, solve this one in a very complicated equation. They solve how the planet was moving. Then Copernicus just to say, if you take the sun as the center, then those planets just surrounding the sun, okay, the equation becomes extremely simple. Okay, just a quadratic, just a very simple equation. And who is right? Because at that time there were nobody can fly over, the Earth. Nobody can see it. But the scientists buy it. Scientists say, if you use, the simple, quadratic equation like an ellipse or a circle, you can explain how the planet moves. You must be right. Okay, the other one use so complicated function cannot be so right. Okay. And of course, later Newton discovered the gravity theory. All things can be explained. But Occam's razor, that one was a very simple way. When you do not really know it, the simple one will win. Okay. So Duncan Watts proposed this. He just say, oh, you explain this network, I explain network. My formula is far simpler than you patch many things on the random network. So my network model is better. Okay. But actually, there are even better ones. We just look at these examples. Then the better one actually was proposed by Barcy Albert and and his major philosophy called preferential attachment. That means not only he gave the formula, he gave the modeling equation, but also he explained the equation why this could be the case. Okay? He actually got a PhD in physics. He really have the physicist rigor, okay, mathematical rigor. Not only show his model, but also explain why. Okay, the why actually come down to the most famous one called preferential attachment. What is preferential attachment? His general idea is this: the network generated was not random. Okay, obvious Dango-Watts also show was not random. Okay, that means a random model cannot work. But how the network really generated? He used this one. He says, actually the model called rich get richer. Okay. Simply says, if you got more nodes, you got more nodes attached to you. Okay. The next time when the new edge comes, the chance to attach you will be higher than those poor ones. Actually, if you think about it, in the internet, there's a similar thing. Okay, that's the one. For example, you get Google. Okay, if you do not know any search engine, what do? You heard of Google, you just Google it. You just attach to Google. Okay, that simply says the Google is already quite rich, but you as a newcomer, very likely you will go to Google rather than go to some no-namer, right? So that's a similar thing. Actually, if you watch the current presidential election, you also clearly see the rich get richer. Okay, simply says this: you can see Republican got so many candidates. Finally, why, for example, Rubio got pretty high? Actually, Rubio got pretty high just because in the previous, the polls. Besides, Trump and Cruz, he was the third one, but he holds a little minor, little moderate view for Republican. Of course, there are a crowd hold this. If you list the candidate, at least 5 or 6 have very similar view as him. But he was ranked number 1 among those people. Okay, those people, you think of those Iowan, they want to vote, they have share a similar view how they vote. They just vote the higher one, right? Because maybe Jeb Bush or others may have the similar views, but they think the winner will have better chance to win, right? So they just voted. That's why his poll boosts up very quickly. Actually, it's almost competitive to Trump. So those are the similar effects. You don't want to vote something to just waste your vote, right? So that's rich get richer is a very popular, philosophy almost in any society, right? So that's the reason he actually, watch this model, he has a preferential attachment principle. Preferential attachment principle says the probability connecting to a node is proportional to the current degree of that node. That means you get more degrees, you have more chance to attract a new degree. So then he used this mathematical model just to look at the probability. It's proportional. I did not write down the formula, but you can easily write formula. It's proportional to your current degree. Okay. Then you generate this model. You will get scalar free. You will get power law. Okay. So that's his philosophy. Mathematically, he proved that, and he worked out this network. The network actually matches the internet, matches this nicely. Then we look at the real world to see which model will win. Okay, you look at so many different ones. The most popular one is a web. Okay. The web, I think Barabasi and Albert, in 1998, they proposed this preferential attachment. In 1999 Nature paper, they really get onto using the soft robot, get a URL, check the internet, and found that you get that many documents in the internet, but their behavior is very much clustered. It's very much like power law distribution. Okay. actually, John Kleinberg in 1999, he really plot the internet, okay, the distribution, like the degree, whether you have one connection, you have, you have lots of different things. He used this K and this connection, the probability. So you probably can see this one actually get very much like, you use those log plot, it's very much like a line. It's only, here you can see just a little twisted, but this one is out degree, this is in degree, both an out and in, they behave like a parallel. Okay. It's not like a Poisson distribution, a normal distribution at all. Okay. So that's John Kleinberg found this. Okay. Of course, I probably should say not everything is parallel distribution. For example, this one is the road network. The road network is not parallel. New York, of course, got lots of roads, but it's not exponentially grows. So you can see that New York, the city, if you get an exponential number of roads connected, the whole city becomes just a road, right? So that's a reason you probably can see, no matter Chicago, Detroit or New York, you still have a very limited number of roads connected to you. So that's not a really parallel. Okay, so this road network is not parallel. But the internet connection, like internet has a few, like a backbone, everybody connected. If you look at the internet connection, like telephone, those connections, they are parallel. They really have, concentration on a few nodes. Okay, so that's, and for this, people actually start studying lots of networks, especially, I think, about more than 10 years ago, I invited Christos Palousos came down here to give a distinguished speech. He came, his whole talk is about the examples of the parallel. He shows so many examples. Most of them are parallel distribution on those networks. You probably see World Wide Web is parallel, citation is parallel. There are lots of things that are parallel. But there's one thing, actually, people study the robustness of the distribution. They actually found that these two different kinds of networks. One is random network, another scale-free network, has very different kinds of robustness. Okay, so this one is a random network, like a U.S. Those you can say the interstate, the road form a network. This is not parallel because you probably see there's nothing, one get exponentially bigger, right? So this one, the interesting thing is you can, suppose during the war, the people want to disable the transportation networks. Actually, it's not easy to disable it because you cut off this edge, they have other edge to go. So it becomes, there's no single node or edge you cut, you will be able to disable the whole thing, okay? Because everybody is sort of equal. So it's very hard you can disable the whole thing, like this. But if you get for example, the hub on the electricity or like internet, things will be different. The first interesting thing is if you destroy the wrong node, for example, the hub nodes and the other nodes, you destroy the other nodes, other connections, it will not affect anything almost because they almost go as well. Okay. However, if you take out those parallel really on the peak, those connections, those hubs, you take them out, you will have very big effect. Right, so because you knock down this hub, there are many things you will not be able to access anymore. So that's people when study like robustness simply say whether something goes down, the things will still run. Okay, they found actually the scale-free network is very good if you destroy anything else but hub. Okay, but if you destroy a hub, you will have very big impact. So That's one. So here, just give you a few interesting. This is the internet visualization. This is their power law distribution. This is the actor, the connectivity. They also follow the power law. Some actors are so attractive, everybody link to them, right? So you will find this. And the citations, some paper everybody cites. Some paper, there are lots of paper and almost nobody cites, get very few citations, right? And co-authorship is the same thing. There, somebody got lots of co-authors. Some people got very few. They also found a power law. The food web and who eats up who, like the top could be like a tiger or a lion or something. Then you're going down. So the food web is also from sort of power law distribution. Okay. The biology map, they found this metabolism, this biochemical reaction in the map. They also found a power law distribution quite a lot, okay, in biology. Like this is biologic pathways, and you probably know, something in the body, you destroy that simple part, you basically kill the person. Right? So those are the center part. And even they look at yeast protein network. You look at yeast protein network, they also found that's published in year 2000, also power law distribution. So that means after, like 1998 was a paper on the power law and the preferential detachment. It's almost like immediately after this, everybody in almost any occupation, any research field, they find lots of power law distribution on networks. Okay. They are publishing around similar years. But of course, there are more things to be discussed. But I will not want to go into the very detail, but I do introduce a very good book you may want to read if you want to go deeper. Okay. The very good book I should introduce you is Christos Faloutzas' book. It's by, I think that's his previous student, Deepak Chakrabarty and Christos Faloutzas. They got an ebook. You can download it. I also put a link. You can follow the link if you are on the UIC account. You follow the link, you can download the whole ebook for free. Okay. That one, the name called Graph Mining, Laws, Tools, and Case Studies. It's a very good book. It's very thin. You can read it probably in a few days. But it contains lots of meat, technical meat. What he introduced, I will just show you. There are several things on the laws of the network. He studies the static network and dynamic network. Static network, he calls static graphs, has power law degree distribution and power law eigenvalue distribution, small diameter, triangular power law, triangular degree power law. Okay. There are many laws. Actually, many were his paper. Of course, the power law degree, he first introduced Barabasi model, that's preferential attachment, but he introduced many others after this. For example, Barabasi model only map on the undirected networks, but the web or many other things are directed. He actually showed a later study on the directed network also is power law. And the eigenvalue also form the power law. Another interesting thing is, if you look at the triads, that means you just not only look at the single node, you look at the triangles they form. He found even those triangles, those triads, also form the power law. Okay, it's very interesting. Many are his research group's research papers, but all published quite recently. You may like to read it. Another one is dynamic graph. That means that the network keep growing, like internet keep growing. Okay. There are some interesting phenomena, because if you strictly follow the Barabasi model, okay, that means you use those random, even using preferential attachment, this principle, you will find if you keep adding new nodes, the diameter will grow. Okay. But actually, to everybody's surprise, they actually studied Yuri Leskovic. That time was a PhD student in CMU. Now he's a professor in Stanford. he got a very famous paper in 2005 in KDD and mentioned their study. They studied the network, the big, like internet or any similar network. He found you put more, when the network starts growing, you put more nodes and edges. The diameter is not growing but shrinking. Okay, so then they actually work out a few new laws. One called a shrinking diameter. I mean, the real net, when they grow, the network diameter is shrinking. And why they are shrinking, they actually found a reason to explain it called densification power law. Okay. Then they actually have the generation model called forest fire network model. Okay. I'm not going to introduce in detail, but I originally want some student to come to grab, Chris Osvaldo's book, some part, to give a presentation because, it's we're not require you to master it, but it's always nice to know it. Another one interesting thing they found in the network model is a weighted network. That means originally the edge, anything is not weighted. Everything is equal to 1. You can think in that way. Okay? Everybody is equal. But in the real network, in many cases, the edges or something, they are weighted. Okay? So if you get a weighted static graph, then they get a snapshot power law distribution. Essentially, that means that the weight degree grows in a superlinear way. It's bigger than linear. Okay? And another one is a weighted dynamic graph. That means if the graph keeps growing, they have weight power law and a principal eigenvalue weighted graph from the power law as well. Okay? But those are a little more involved, a little more complicated. If you are interested, you can get into his book. You can read a little more. I will not introduce his whole book. But one thing I really want to introduce is this famous paper. This paper got the Best Paper Award in KDD 2005. And I think they also got the highest impact paper award in 2015. Okay, that's 10 years. After 10 years, this paper is one of the, I think they total give, in KDD history, they total give 6 papers as the highest impact paper award. And this one is the youngest one because you can see you have to have more than 10 years history. The 2015, this KDD 05 is the earliest one, the latest one you can get. And this paper, graphs over time, got the award. What they discovered, I probably can show you this. They discovered is in the real network, okay, they have another law besides this preferential attachment. Preferential attachment basically say, if you get an edge where you want to add, you have a higher degree, you have better chance to attract new edges. Okay. This densification power law basically say, if the graph start growing, the number of nodes added is smaller than the number of edges added. Simply says, you just think about the internet, they grow. Actually, they grow more on the edges rather than the nodes. Okay. That means they have a superlinear property. What is superlinear? That means originally you were thinking if the nodes grow like double, the edges also will grow double. Actually, edge will grow more than double. Okay, so that's superlinear. Okay. They actually check the formula. You can see this is number of edges. This is number of nodes. If it's a linear, you will get a proportional. This one is a k. Okay, that's a linear. But actually, it's more than linear. It means this beta is a little bigger than 1. Okay, you can see. They check the real beta is 1.07 to 1.03 to 1.07 in many real graphs. Simply says it grows not quadratic, but it's definitely bigger than linear. Okay. So what this effect? Because you grow more edges than the nodes. Actually, you make more things, when you grow, you make more things connected. That's the reason you shrink the diameter. Originally, you have that far to reach it. Because you get more edges, you actually take a less effort to reach it. That's why the whole network grows, but the diameter actually shrinks. So it's very interesting. Not only they found the diameter shrinks, they also have a theory to explain it. Okay. The theory basically says there's a densification power law. That means to grow the edges is more than the nodes, than the vertices. That's why the whole diameter actually shrinks. Okay. And not only they found this diameter shrinks, they found a new generative model, which is a revision of Barabasi's preferential attachment model. That means they say that the original general philosophy of preferential attachment is still right, but you have to revise it. Okay. How to revise it? They found a new model called forest fire model. What is forest fire? That means when the graph started growing, okay, these nodes were attached to another node. The Barabasi one just say you get 10 times more edges, you have 10 times more probability to attract this edge. It's very simple, but you cannot explain the diameter shrinking. What they said is they pick up a node. This node is the forest fire starting point. Okay. But the forest fire starting point, they start burn. They burn in a way it's like a forest. Okay. They burn. They go out, but they also go inside. If you watch the forest not only just a spread, they burn more thoroughly inside, right? So they actually use this forest fire model. The process in a mathematical function, they basically say there's an in-link property, there's an out-link property, and they have different proportional probability. Then they use this model to model the internet growth. They found it's very nice. Okay, that's why they got this new model to explain the diameter shrinking. And all these things are in one paper. Okay, that's the reason. He, that time, was a student, was a PhD student in CMU. But he grabbed these two very powerful ones. That's his advisor. That's John Kleinberg, actually was doing sabbatical, and he went to CMU. They worked together. They worked out this model, this new law called a densification power law. And it really shake all the reviewers. They really loved this one. So that's a very clear vote. He got the best paper award. Of course, even now, he's the star in Stanford, very young. Okay, so that's the whole thing I introduced about the recent history about network model the real network, internet, and many other networks. Okay, so this one, if you guess where it is, this actually was in Athens. Athens, in the center of the downtown, they have a very, very ancient building on top called Acropolis. The Acropolis, this one was built like 3000 BC or something like this. It's just very, very old. You know, most other nations even do not really have a recorded history. And it was a very nice one. Of course, they repair some part, otherwise it become almost like a ruin. But even now, they use it for some performance. You can see, you can all sit here, and the performance can be here. This, of course, this building was like already rebuilt somehow, but it's a lot of part already gone, because originally it could be much bigger. But anyway, it's very nice. If you go to Athens, of course, Greece now economically in trouble, but they attract lots of tourists. You probably see the Acropolis, and their museum is really great because many of them is several thousand years BC. I think this one probably is not 3,000, but 1,500 BC. But it's still very, very old. They do have some 3000 BC ones, but it's a little more primitive. But it's very, very impressive because so old one, you get so nice things. Okay, because you go to Rome, you see like the first century or 100 BC. But this one you see like 1000 BC. That's very different. Okay, so now we got a little time. I just give you a very short introduction of social network. Why I give you a very short introduction instead of a very long introduction? Just because social network, we are going to discuss later, we use heterogeneous information network model. And this social network, many people studied using homogeneous model. Later, we are going to show you use heterogeneous model, you are more powerful. Okay. But this one, I just show you the social network. Most people modeling is using just nodes and edges. It's a graph. You can model social network. There are many, many social network sites. Of course, I wrote this a few years ago. Now it probably is totally outdated because MySpace is gone already, right? You probably can only see Facebook and LinkedIn. Delicious probably is gone also, but YouTube becomes very big. There are many new things like Pinterest, I think even Uber or something, you can put it down there. They are a social network as well, right? So this is a logo of many, many social networks they put together. I just grab it from the internet. But there are lots of things. You see there are many different ways to do the Web 2.0, like blogs, wikis, social networks, digital media, social tagging, and many others. Actually, Twitter and Yelp now become very big already. Right? So if you look at social network versus the block sphere, like people just put things there, like wiki things, that's still different because social network get lots of the friendships putting together, right? So there's another book, if you like to read, in the same collection on Morgan Claypool, is Huan Liu. He has a social network book on the web. You'll probably see I introduced in the same place, Morgan Claypool on a data mining site. One I just introduced you is Christoph Falusa's book. Yizhou San's book is there as our more like a semi-textbook. This Huan Liu's book is about a social network. Actually, this one I grabbed from his book. His tutorial notes are also in the book. The difference between friendship networks and block sphere. You probably see the block sphere basically is you get a person to group, okay, or to some blog website. But the friendship network is person to person. You get a very close link, and it's very, very popular now. And the first thing is we know there's 6 degrees of separation. I mentioned this small word many, many times. And it really got into like a, Arabic revolution or something. It's also, around. I think the Facebook and all these play the role or something. The communication network you probably see is also in the same, the biological network. They all have the similar models. So in general, I should say this is a very big domain. Actually, when Yuri Leskovic, who graduated from CMU, at CMU, his major thing is doing network modeling, study a lot of networks. Once he joined Stanford, his major study becomes social network. Study a lot of things on the social network if you read his most recent papers. It's very dynamic field because the social network is a new thing, and there are many, many new research papers. There are dedicated conferences called ASNM, is Advances on Mining Social Networks, or whatever. I forgot the exact acronym, but it's on the social network itself. Okay, but the detailed thing I'm going to introduce more on the heterogeneous information network model. Simply says, social network you can treat like a web. It's everybody is just the same. The node is the same. But actually, you should think a little more broadly. Is social network, many things are heterogeneous. You link to your friends on the Facebook for different purposes. Think about it. Some are your personal friends, your family members, but some could be your old classmates. Some could be your research friends, or some could be your life friends, like biking, or go to restaurants together, or have party together. So that's a very different way. So you have to think about the link is not simple link. It contains more information, contains heterogeneous information. That's the reason for us, we are going to take the heterogeneous information network model as a major model. We're going to study it. Okay. So I think I basically finished this one. The thing I probably want to mention is there are many more things you can read. Okay. If you, for example, we already passed this chapter without anybody doing presentation. But feel free, if you want to present, you say, oh, I did not know there's something not covered, like Crystal Fellows's, these different models are not covered. You want to study it, you want to give a presentation or give a survey, you're welcome. We can even patch you to the later one. That means you can give a next lecture or the lecture later. You can, if you say, I spent the whole weekend, read through Crystal Fellows's book, I want to give a presentation, you let me know. Another interesting thing I should mention before I finish is the homogeneous network model, the graph model on the generation, like a different model, like a Barbasi preferential attachment, like a forest fire. Those things have studied very thoroughly. However, in the real network, there are many networks are heterogeneous network. Just give a simple example, you take patients, doctors, hospitals, disease, genes, drugs, or all these things you link together. That's different from the web page link to the web page. You have very different groups of things you link together. You form a heterogeneous one. The heterogeneous network model, how to model it, how to generate it, whether they follow the power law, whether there's a forest fire, or how they grow, what kind of statistic modeling you should get, nobody studied it. Okay. I think actually it's a very interesting. I remember 2 or 3 years ago, I asked one of my PhD students, say, whether you want to study it. She actually looked at it, and she says, oh, this is the likely power law. But so far, interestingly, there's no research paper even on it. Okay. So if you're interested in just take this one as your research topic, it's also good, okay, because we do need such model. Okay. So that's the one. Then I just finished everything, I think. The last one is still, this picture is Notre Dame in Paris. So I took all those pictures in Europe. I just show you one set in Europe. Okay, so remember, if you come late, you did not sign. I think the sign-up sheet is over there. You should sign it. Okay. Another thing is I give the homework today. You should look at it. Thank you.